Hello, ZK Summit. It's a pleasure to be here. I'm Jim. I'm the CTO of Ulvetanna and co-founder. And if you've heard of us before, you probably know that we are also building specialized computing hardware for ZK proving, much like the companies Justin mentioned in his excellent talk before this. And we completely agree that specialized computing tasks like ZK proving require dedicated, specialized proving hardware. Our efforts have been focused on FPGAs, which are field programmable gate arrays. This lets us use native digital logic while still being able to iterate quickly. But Ulvetanna is not just a hardware company. We are a cryptographic acceleration company. So what do I mean by that? Well, high-performance computing needs fast and efficient hardware, yes, but it also needs finely tuned software and optimized algorithms that are all designed to work together. This is known as hardware-software co-design. And this basically means we don't just want to take an algorithm and a software implementation and go build an ASIC for it. We want to look at this from a hardware-software co-design perspective, and that's what led us to do the research and implementation of Binius, which is a new SNARK based on towers of binary fields, which I'll be talking about today. But quickly, I want to give a couple of examples of hardware-software co-design that you might already be familiar with. So we can look at the industries of storage and machine learning for two examples here. So in the world of storage, we used to have hard disks, and now it's, SSDs, solid-state drives, and NAND flash are extremely prevalent. And they've led to a huge improvement in I/O performance. If you don't believe me, just try running an Ethereum node on a hard disk and let me know how that goes. But they appeared at first to have a big problem, which is that writes to the same memory location with NAND flash wear down the hardware very quickly. And so this required the industry to build a firmware and software stack above it to work with the hardware to do what's called wear leveling, which makes sure that writes to the same logical location actually go to different physical locations so that the flash doesn't wear out. We can also look at machine learning, where Google created this tensor processing unit, and their first generation of the TPU did not support 32-bit floating point arithmetic, which is what many ML models were using. Instead, they decided to use 8-bit fixed point quantization and forced the model developers to use this as well, simply because 8-bit fixed point computation is far more efficient. According to their blog post, this let them fit about 25 times more multipliers. So the point is, these are examples where the hardware design feeds into the software design. So where do we start with hardware-software co-design? We need to start by profiling the options that are out there. So Ketchak is a really good benchmark because it's the #1 challenge and bottleneck for team scaling Ethereum today, and that means that there are widely available benchmarks that are optimized for it. So we can look at Scroll and Plonky 3's implementations. Scroll uses Halo 2, which is a Plonk protocol KZG commitment scheme with the BN254 curve, and Plonky 3 uses the Fry commitment scheme with a 32-bit field. And what we can see here is that the proof size is about 50 times smaller for Scroll, but the proving speed is 10 to 15 times worse. Plonky 3 can be run in one of two modes, using either Ketchak, which is a faster hash function, or Poseidon 2, which is more recursion friendly. So we're going to focus on Plonky 3 primarily for the remainder of this talk. I need to give a little bit of an overview of where proof systems spend their time. You have 4 key steps. Generating the witness is basically storing the trace of register and memory states over time. It's not particularly computationally expensive, but it's a bit tricky to parallelize. Committing the witness is basically like fancy hashing. In the case of Plonky 3 and Binius, this is applying an error correcting code and hashing the trace. There's the vanishing argument, which is either a polynomial divisibility check or the interactive sum check protocol. It basically computationally boils down to lots and lots of polynomial evaluations or arithmetic circuit evaluations at different points. And then there's the opening proof, which is kind of like where the crypto magic happens, but actually we're not going to worry about it too much. The time to do the opening proof is usually not super significant because it can be batched over multiple polynomials, which amortizes the cost. So when we look at like where Plonky 3 is spending its time, it just immediately jumps out that commitments are what we need to tackle first. It's, you know, the Plonky 3 prover spends almost half its time doing commitments with a fast hash function, Ketchak, and almost 75% of the time when using Poseidon 2. And so I can't go into all the details on Binius, but what I want to convey is that if we want really, really fast, verifiable, and zero-knowledge computing, I'm going to argue that binary fields are the right fundamental primitive to be building this on. And that's for two reasons. Basically, they give us very efficient arithmetic, and we can get very efficient arithmetization. So starting with finite field arithmetic, we have two common classes of finite fields. There are prime fields and binary fields. Prime fields are probably more familiar. These are numbers, the integers modulo some prime number. Binary fields might be less familiar. The most fundamental binary field is F2. It's the field with 0 and 1 of bits. And then for any k bits, we can define a binary field that fits in exactly k bits. And you know, this is different from prime fields. So prime fields don't have a canonical representation in k bits, meaning when we're talking about a 32-bit prime field, this means it fits within 32 bits, but not that every 32-bit string maps uniquely to a field element, which is actually a really convenient property that binary fields do have. Integer prime field addition is just integer addition with a conditional subtraction, whereas with binary fields, this is a bitwise operation. It's XOR. Oops. Oh, how do I go back? Multiplication of prime fields is basically integer multiplication with a reduction method. There's a lot of options here, but basically unless you have a special form of your prime, your reduction is going to incur more integer multiplications, whereas in binary fields, the multiplication operator is polynomial multiplication. Again, not going to go into the details, but what I do want to make clear here is that multiplication in binary fields is carryless. So, like, remember back to grade school when you were learning how to like add and multiply numbers by hand. You have to keep track of the carries, and then the last digit that you have depends on all of the previous digits. And the same exact thing happens in digital circuits. You can see how the last output bit of an integer multiplier depends on basically all of the previous computations. So the total dependency path is really long, and in circuits, this creates propagation delay of the signal, which limits the maximum clock speed that you can run these multipliers at. Whereas binary fields, basically all of the output bits are sort of computed independently based on a small number of input bits, and they're combined using XOR gates, whereas the integer multiplier needs these much more expensive full adder and half adder boxes, which is what HA and FA mean there. Another fun fact, squaring in binary fields is just really cheap. It's just a crazy math fact that in binary fields, x plus y squared equals x squared plus y squared. And so when you're multiplying, or when you're squaring field elements, the number of cross terms in terms of bits or limbs that you would need to compute is much lower. It's just this diagonal, as we can see in this representation. So the thing is, like, binary fields are not a secret new technique in cryptography at all. They're very commonly used in cryptography. If you've seen one of those, the QR codes, well, guess what? They're using binary fields. They're using Reed-Solomon error correcting codes over binary fields. They're used in the AES encryption standard. They're used in the GMAC, which is used in AES GCM mode. Binary field elliptic curves is a very well-studied field for hardware efficiency. The original Fry and ZK SNARK protocols were defined for binary fields. And one primitive that you might not be aware of is Grostel, which is a hash function that appeared in the SHA-3 competition as a finalist, along with Ketchak and Blake 2. It's based on the design of AES, and it's particularly interesting for us with use with Binius because it's fairly recursion friendly, while still being, a fairly classically defined hash function, natively based on f to the 8. So I'm not going to formally define what tower fields are, but they are a type of binary field that is not used in any of those previous constructions that we identify as being really, really good for SNARKs and having lots of interesting benefits. And so I'm not going to define them formally, but I'll kind of show you how they behave. So we can take a string of 128 bits, and as I said, we can interpret this as a unique element of the 128-bit binary field, or we can interpret these 128 bits as a vector of, say, 2 64-bit tower field elements, or 4 32-bit tower field elements, or 16 8-bit tower field elements, all the way down to 128 1-bit F2 elements. And this is all, doesn't require any computation. This is basically a typecast on a string of bits, which is a really interesting and useful property, and we make use of the fact that we can pack small field elements into larger ones with no computation over and over throughout the design of the Binius protocol. In terms of computational efficiency, here are some of the kind of asymptotics of implementation. We can see that Fan and Parr identified this particular construction of a tower as having really interesting computational properties. We can do multiplication of field elements with the same asymptotic complexity as Karatsuba integer multiplication, which is subquadratic. Inversion, crazily, is the same asymptotics, and our FPGA prototypes show that it's only 1.5 times more expensive than multiplication in digital logic. And something that's really important for us is because the fields contain these subfields, if you want to multiply a large field element by a subfield element, it's basically linear in the size of your large field element, assuming the small one is constant. So asymptotics, we know, are good guideline, but we also get really good concrete performance. So CPU benchmarks we have show that our implementation of binary tower fields with SIMD optimizations actually outperforms BN254 scalar field ops and the quartic extension of Baby Bear. I should say that all of these benchmarks are for cryptographically large fields, 128-bit extension fields, because that becomes the bottleneck in the sumcheck protocol. Now, the quadratic extension of Goldilocks is also really fast. That's 200 mega multiplications per second. But actually, there's a binary field called the polyval field, which is itself not a tower field, but it is isomorphic to one. And we're able to leverage this in our sumcheck prover. So we can operate conceptually over the 128-bit tower field, but use the explicit isomorphism into polyval to get really, really fast, high throughput binary multiplication in the 128-bit security parameter. So this is pretty good, but really the FPGA numbers show the real benefits here. So our team is working on FPGA implementations of this, and here are some numbers. So starting with Mersenne 31 as a baseline, which is about the most efficient prime field operation you could do, or that we see in SNARK land. We can't just compare throughput the way we did with CPU, so the way to interpret this is we want to look at the number of logic gates required and then the maximum clock frequency that this could run at, and this lets us derive this area times delay efficiency metric that we have to compare them. So we see that a 32-bit binary field multiplier is about 5 times more efficient than the Mersenne 31-bit prime field multiplier. When you go down to the 16-bit tower field, which we're able to use for Reed-Solomon encoding, in many cases, it's another 5x more efficient. And even the 128-bit tower field, which is 4 times bigger than Mersenne 31, is only like 2.5 or less than 2.5 times less efficient, even though on its face you would think that it should be 16 or 9 with Karatsuba times less efficient. Our numbers for the BN254 estimate did not make it onto this slide, but one thing I should say is all of these multipliers complete in 1 clock cycle, whereas our BN254 implementation requires 49 clock cycles pipelined to complete, and our resource utilization estimate is that it's 200 times more gates to do a BN254 multiplication than the 128-bit binary tower field. So when you go to especially big integer multiplications where you need to propagate these carries, the benefits of this really shine. Here's like a cool thing we're working on, a bit of a preview of some upcoming work that brings together a lot of the efficiencies of binary arithmetics. So the vision hash function is an arithmetization optimized hash function. This was not designed by us. This is from a paper from 2019, the design of symmetric key primitives for advanced cryptographic protocols. But it uses squaring, inversion, and matrix multiplications. And we have been collaborating with 3MI Labs and Tomer and Myron over there to create an optimized instance based on tower fields where we get additional computational properties. So our S-box can be optimized with fast inversion from the recursive tower field construction. We can use the squaring in our arithmetization, which, as I said, is very fast. And the MDS matrix multiplication uses the fast subfield operations that I mentioned. And not only that, but we can use additive NTT techniques to make this matrix multiplication extremely fast. So we don't have benchmarks yet. This is a bit of a preview of some upcoming work, but we're very excited about this construction that will let us have really recursion-friendly hashing. So moving on to efficient arithmetization. How do you arithmetize Ketchak? So Plonky 3 uses air arithmetization, and here's just a bit about how that works under the hood. Each Ketchak F permutation occupies 24 rows of their trace, and each row has more than 2,000 columns. It has 2,300 columns with 1-bit values and 400 columns with 16-bit values, and the total number of nonlinear constraints that you need per row is about 1,000 to evaluate in your vanishing argument. And when I say 1 or 16-bit columns, STARKs need to occupy full field elements. So you need to pad these 1-bit columns up to 32 bits. So on its face, this is nearly a 32x loss of efficiency right out the gate. And this is what we're basically trying to capture with packing. And so that phenomenon is what we call embedding overhead. So kind of the question is, do we have the ability to commit small values faster than large values? And actually with elliptic curve commitments, the answer is yes, with some caveats. The MSM algorithm basically scales linearly in the size of the scalar. It starts to break down when you get below like 10 bits, depending how much work you want to do on your MSM optimization. And then with Fry, the answer is basically yes down to 32 bits. And this is because of a fundamental property of Reed-Solomon codes, that Reed-Solomon codes require a field that's larger than your trace size. And so for practical reasons, we basically, this caps out at 32 bits. With Binius, basically we get great scaling of committing small values down to 1-bit values. We can commit F2 elements, which are single bits, nearly as efficiently basically paying by the bit as opposed to larger field elements. And the way I like to think about this is that the Binius polynomial commitment scheme basically maximizes the information density of your committed data, which is really important because we saw that commitments were so slow. So now to actually talk about what Binius is. This is a system we've been developing in software, and we wrote a paper that came out in November called Succinct Arguments Over Towers of Binary Fields that includes the kind of key research contributions. we talk about an arithmetization for SNARKs over towers of binary fields. This uses a multilinear polynomial IOP based on hyperplonk. We generalized the breakdown polynomial commitment scheme, and in a follow-up work that we published just last week, also generalized the Frye commitment scheme to work over binary fields in a way that eliminates the embedding overhead. So lets us commit very small elements with high efficiency. And we also have a few other contributions from that paper. We add some new gadgets for general multilinear arguments, including a very efficient shift argument and an adaptation of the lasso lookup argument that's able to capture some of the uniquely good properties of the lasso lookup argument in the kind of world of linear codes and hash functions. So to say a bit about how we're able to avoid this embedding overhead. I can't go into full details in this amount of time, but very roughly the idea is we're leveraging the packing property of tower fields that I talked about earlier. So let's imagine that we wanted to apply breakdown to the field F2, which is single bits, and how you would apply the standard breakdown argument to this. Well, you need to do a Reed-Solomon encoding, which let's say you need a 16-bit field size to do that. So typically you would pad that 1 bit up to 16 bits. The prover would then send a linear combination of the pre-encoding messages to the verifier. And then during the consistency testing phase, the verifier needs to open random code word locations to test consistency of the prover sent linear combination with the originally committed message. We generalize this, so instead of padding, we take chunks of 16 F2 coefficients at a time and pack them instead into 16-bit field elements, and then we apply the Reed-Solomon encoding to that. So that's already 16 times more efficient, and then during the consistency testing phase, instead of opening single columns at a time, the verifier needs to open chunks of 16 columns at a time and test it with chunks of 16 adjacent symbols in the prover sent message. And this is, able to go through and doesn't have a substantial performance penalty over, something like using a regular binary code or using the same techniques. As I said, we've also been able to generalize Frye to work with low and no embedding overhead in the commitment phase, which is, I think, very cool. And conceptually, the way to think about where this is coming from, we're not, strictly speaking, doing a Reed-Solomon code that requires, that's a linear code over a field. Instead, we're doing a linear code applied to vectors of these tower algebra elements, which are defined in our paper. They're basically vectors of field elements. And yeah, so to say a little bit about how arithmetization now looks in Binius, we're able to arithmetize Ketchak in a fairly different way with many fewer committed columns and many fewer nonlinear constraints. Instead of each permutation occupying 24 rows, it occupies 1,500 rows over F2, but we can also virtually view this as 24 rows over F2 to the 64. K should be 64 there. Each row has only 60 committed columns, and then we have 80 virtual columns, which are basically non-committed multilinear polynomials that we can still evaluate efficiently via the sum check protocol, which is very efficient for the verifier and prover. And pictorially, this is kind of what it looks like. So here is our trace. We have the input state, which is a vector of 25 64-bit field elements, or 64 rows. The output state, we also commit these C and D sort of auxiliary states, and then we have C prime and B prime, which are not committed. They are virtually defined columns that are defined as cyclic chunk-wise, bitwise shifts of some of the other columns, which is basically exactly the operation that Ketchak needs in its definition. And then we can just constrain that the output state of one round is equal to the input state of the next round. So where does that leave us with respect to performance? Well, our proof sizes are between 2 and 3 times bigger currently than Plonky 3, but our proving performance is already about half, and we expect that to get better over time. And this is all measured on a GCP instance with 11 physical cores. But really, I think the interesting thing is looking at where our prover is spending its time. We've basically completely eliminated the commitment bottleneck and created a new bottleneck, or we're left with a new bottleneck in the sum check protocol. And so the sum check protocol, as I said, is just a matter of pushing lots and lots of polynomial evaluations and field multiplications, which we intend to believe we can tackle extremely efficiently with dedicated hardware, and so that is what you should expect to see from us, which is extremely fast proving using hardware-software co-design with the sum check protocol accelerated in FPGAs, and very low memory usage proving. So that's all I have for you, and I hopefully have some time for questions. You can follow us here, and yeah.
Alrighty, yeah, we have a few minutes for Q&A, and just so you know, we have a break on right now. We're running a little bit behind, but yeah, we can take a few questions. Any questions? Oh, there you go. Oh, man in the back. Yeah, sure. He raised his hand. I was trying to get it. Go ahead. There's a microphone on your seat.
You can take this.
You can take this one.
Okay. And what is performance related to non-native fields like scalar fields or binary ring like native CPU types, integers?
I'm sorry, where am I, where are you seated?
Yeah.
Oh, yeah, sorry, could you repeat that, please?
The question is, what is performance related to, what is performance? Sorry. What is,
This is.
what is performance with non-native fields like integers?
Yes, that's a great question. Like, essentially, how do you arithmetize native integer operations like integer addition and integer multiplication, is the question?
Yes.
Yes, so our strategy is to, we can do integer addition by just basically bitwise decomposition. So we do need to pay for that in the sum check protocol, but with small field sum check optimizations, we expect that to be pretty good. We took down the benchmarks for that just because they were a little hard to maintain, and we prioritized the catch-act. But essentially, you can do integer addition with only one auxiliary committed column, which is the carries. And then integer multiplication, we are intending to do with the lasso lookup argument. So we would use lookups for 8-bit multiplication of limbs, and then essentially add them together. So we don't have benchmarks for this yet. There's a description of how these gadgets work in the paper.
Okay. Thank you.
Yep.
Testing. Here.
Thank you. Thanks for a very interesting presentation. So 2 questions. You showed that Ketchak, as arithmetized with binary tower fields, it's more efficient than Poseidon, for example, right?
Oh, well, certainly it would be more efficient for us to arithmetize Ketchak than Poseidon, just because Poseidon's defined for prime fields. And but
right.
You know, what I tried to show with the vision hash is that there are, similar to Poseidon, arithmetization optimized hash functions for binary fields, and we've been investigating one called vision.
Right. Do you expect that your vision arithmetization will turn out to be more efficient than Ketchak?
It's a really interesting question. In terms of prover speed, I think they're actually both going to be very fast. The main benefit to vision is that the proof sizes will be smaller. So one thing about embedding overhead, we talk about eliminating embedding overhead in the commitment phase, but still doing polynomial commitments and opening proofs for small coefficients results in higher proof size. So the nice thing about vision is that it's natively defined over a 32-bit field, and so we would expect the proof sizes resulting from that to be smaller than Ketchak. So that's the main benefit that I see.
Right. And also, second question. So there is a huge research now in arithmetic hashes like Poseidon, but also MIMC and Griffin and other hash functions. So do your approach suggest that maybe it's the wrong direction to go? Maybe we should focus on binary fields, like versions of hash functions over binary fields rather than prime fields?
Yes. I think that everything should move to binary fields. No, I mean, I think that especially for symmetric cryptography, this was one of the things that led us to pursue this, that we realized how expensive arithmetization optimized hash functions were for prime fields. Our results in FPGA acceleration of the SNARK protocols highlighted this, and all indications were that arithmetization optimized hash functions for binary fields, of which Grostel could sort of be interpreted as one, are just more efficient for arithmetic reasons.
Right, yeah, thank you.
Do you have an estimate of how much faster like vision is in the FPGA versus like a FPGA implementation of something like Poseidon?
You should talk to Danilo. We don't have that publicly available yet, but you should come find us.
I think we have time for one more question, if anyone has one. No? Okay, so we're on break now, and we'll be back in this room. Round of applause.